In today's video, we are going to look at the other side of the materials topic, and that is that of fluids and what happens when an object moves through a fluid. In order to really fully do this properly, we need to think about density, which is a topic that we covered at GCSE. And so we know then that density, given the symbol rho, is mass divided by volume. For our purposes here, the mass is important because it is what determines the weight of an object. And the volume is important because it determines how much of a fluid the object will displace. This displacement is very important because it leads us to Archimedes' principle. Archimedes' principle says that when an object is wholly or partially immersed in a fluid, the upthrust experienced by that object is equal to the weight of the fluid that's displaced. Think about this in terms of the density of the fluid. For a denser fluid, we will have more weight for every volume. And so when you put an object in that fluid, we are going to have a higher weight of displaced fluid and therefore a higher upthrust. Remembering, of course, that weight and upthrust are both forces and so are measured in newtons. If, on the other hand, we have a denser object, that means it has less of a volume per kilogram or per newton, and therefore it's going to displace less of the fluid and therefore experience less upthrust. So you can see that whether an object floats or sinks, whether wholly or partially, depends on the relative densities of the object and that of the fluid. So in this example up here, this volume of this object is enough to displace that much fluid to provide enough upthrust to balance its weight. And of course, a denser object of the same volume would need to displace more fluid in order to balance its weight because its weight would be greater. So it's this connection between fluid density and object density that determines this. Now let's talk about viscous drag. So we've met viscous drag before, although we may not have called it that. This is what at GCSE we called air resistance or water resistance. Now we're just going to put it under the general banner of viscous drag. And there are a few things that the amount of viscous drag actually depends on. The first thing is the viscosity of the fluid. This is how thick or runny it is, how viscous it is, how easily it flows. And this is temperature dependent. So with liquids, as you increase the temperature, they become less viscous. Think about warming up honey. It flows better, it becomes runnier. The opposite is true with gases. As you increase the temperature of a gas, it becomes more viscous. The second thing that it depends on is whether the liquid or fluid is in laminar or turbulent flow. I will come back to laminar and turbulent flow in a moment. We'll just consider the rest of the factors that the viscous drag might depend on. Number 3. Obviously, the faster the object is moving through the fluid, the more viscous drag it's going to experience. And number 4, something that we already intuitively know, its size and shape. So it depends on how much of the liquid it's going to be pushing against, and obviously we know there are objects that are streamlined. These two diagrams here show us visually very clearly the difference between laminar and turbulent flow. So laminar flow is generally slower. The paths of any particles or layers within a fluid, the fluid do not cross. And so it flows in these parallel layers. Turbulent flow, on the other hand, you have these particles of the liquid as they're moving along. Their pressure and speed at any point during the liquid is constantly changing, both in magnitude and direction. So you get some particles that will be coming in the opposite direction than an object might be moving through it, and of course that's going to increase the viscous drag. So we have lower viscous drag here, and I'm just going to use FV for viscous drag, and higher viscous drag down here, obviously, because we've got some particles that are going to be going in opposite directions. Which brings us along to Stokes' law. So Stokes' law is a law that allows us to calculate how much viscous drag there is for these various properties. And so again, using F with a subscript of V to represent the viscous drag, Stokes' law says that viscous drag is 6 pi eta RV. These are our factors. Eta here represents the viscosity of the fluid. And that is given in units of Newton per meter squared second, or more usually Pascal seconds. And again, that is temperature dependent. R is the radius of the object. Now, one of the conditions with Stokes' law is that it only truly applies to spheres, hence the radius. It loosely applies to other shaped objects, and so we can model a lot of the objects that move through a fluid as a spherical object, but you do need to realize that it only actually applies to spheres. And then v, of course, is the speed of the object through the fluid. The other condition that goes with Stokes' law is that it only applies when the flow is laminar. So we don't have an expression in here that considers what the viscous drag would be under turbulent flow, because it's too difficult to predict. There are a lot of variables with turbulent flow, and in fact it's not terribly well understood yet. So it isn't considered in this equation. Okay, now let's look at applying Stokes' law for objects that are actually moving through a fluid. And of course, the classic direction that objects tend to move when you drop something into a liquid is going to go downwards. So we're going to consider first the situation when an object is moving down through a fluid. And throughout all of this, we're going to remember that mass is density times volume, and that the volume of a sphere is 4/3 pi r cubed. Because of course, if we're going to apply Stokes' law, we apply it to spheres. So in this situation, this object is falling through this liquid, and it is falling at terminal velocity. And we can see the forces labeled on this diagram here. So we can say, if it's going at terminal velocity, it's not accelerating, and therefore all the force downwards is balanced by the force upwards. And we can say mg is equal to our Fv, that's our viscous drag, plus our upthrust. Now let's remember what upthrust is. Upthrust is the weight of the displaced fluid. So that means that upthrust is equal to the mass of the fluid. And again, I'm going to be using subscripts through here, F for fluid and O for the object in there. So upthrust is the mass of the fluid times G. But let's remember that the mass of the fluid is the density of the fluid times the volume displaced. And the volume displaced is the volume of the actual object that's in there. So again, we're going to solve that. Upthrust, we have the density of the fluid times the volume of the object times G. And so we can substitute that into our equation. Now let's consider the object itself. So the object is falling through the fluid because of its own weight, and its weight is mg as we've written here. But of course, the mass of the object is going to be the density of the object times the volume of the object. So we can replace this with density of object, volume of object, G, is equal to the density of the fluid times the volume of the fluid times G. And in here we will put in our Stokes' law equation, which is 6 pi eta RV. One more final substitution. We can replace all these volumes with the same expression, 4/3 pi r cubed. And because both of these are the volume of the object, the radii are going to be the same. So we end up with 4/3 pi r cubed. Now, of course, that's the very long-winded version of it. You could be given just the volume of the object, in which case you wouldn't have to go down that final step of replacing the volume with its expression there. But from this, of course, you could, depending on what you know, you could find the density of the fluid, you could find the viscosity of the fluid. You just need to rearrange and solve. Keeping that in mind, let's think about what happens if the object is actually moving up through the fluid. And this is quite a common exam question because people are so used to just thinking about objects dropping through the fluid that they forget. Bubbles, for example, rise up through a fluid, and the same sort of equations can be applied to them. But of course, this time, our mg and our viscous drag are going in the same direction, and only upthrust is going against them. So we need to identify now and remember which part of this expression was which. So this was the weight of the object, this is the viscous drag, and this is the upthrust. And we can use the same expressions. You could derive them again, but as we've derived them once, it seems sensible just to use them again. And this time, our mg plus F is going to be equal to the upthrust. So if we were to rearrange that, we get... Do be very careful and make sure you are using the correct version. And it's always a good idea to start from thinking about the three forces that are acting, which direction they're going, and then if you have to derive, go from there, rather than just trying to remember these equations. There's no point in trying to learn this off. You'll make a mistake. Think through the logic of it instead. You can do it pretty quickly if you make yourself practice it a few times.